So in this lecture, we'll talk about embedded systems and how they are related to IoT devices. There's a lot of overlap. Embedded systems, the term usually refers to not just how the device is used, but also how it's implemented, how it's built. So there's a lot of overlap between the two terms, and IoT devices are typically embedded systems also. So we'll just define that and give you an idea of what embedded systems are. It's good to know the term embedded system because it's still commonly used, and what we're building are typically embedded systems. What we'll talk about building later in the class, they're actually usually embedded systems. So what are embedded systems? Embedded systems are systems, they're computer-based systems that don't look like computers. Okay, that's my simple definition. The complexity of a computer is hidden from the user. So if you have a computer, desktop, laptop, something like that, if you've ever used it, which I know you have, there are complexities to using a computer. So say you want to install some new software, right? You install software, sometimes it's easy, but sometimes there's a conflict. Like, for instance, video games. I used to play video games on computers. Now I use only game machines, but say I play a video game on a computer. I put the video game in there, install it, and it has some conflict with the video card. I need a new video card, right, to play this new video game. So then I need to get new drivers for my video card. So there's this interaction, right? The functions are not separated. Right? This is different than an IoT device. Or an IoT device, it basically has one function. We talked about this last module, right? It has one function it's trying to do, like a car. It does car things, right? A camera does camera things. But a general purpose computer, it can do a lot of things, and so there can be conflicts. So if I install software to play a video game, that might interfere with the software to do something else. So these relationships add to complexity, right? And so it makes it harder to use a standard computer than it is to use, say, an IoT device. Now, an embedded system, and IoT devices are generally embedded, they hide the complexity from the user. So the picture we got here, this is some kind of a scale, let's say. And say it's an IoT scale. So the user doesn't have to see the complexity of what's going on inside. The user just knows how to use it. So it has a very simple interface. And and this is where the term embedded comes from. The complexity is embedded inside the device. The user doesn't have to deal with the complexity. So that's what an embedded system is, how the term came about. Now, these embedded systems are much more common than desktops or laptops because there is computational ability built into a lot of different devices. Now, one thing to notice about embedded systems that's necessarily different, not necessarily, but can be different than IoT devices. IoT devices are almost always connected to the internet, thus the term Internet of Things. Embedded systems may or may not be. Embedded systems may have computational complexity in there, but no network connection at all. And so there are a lot of uses for devices like that. Things are moving from embedded to IoT because of the trends we talked about in the last module, the fact that internet connectivity is so ubiquitous and it's pretty cheap to attain. So a lot of these devices that used to be just embedded are now becoming networked, and so you would call them IoT. So what are embedded systems? They're basically everything that interacts, all the Internet of Things devices that we talked about, but plus or minus the internet part. So take a digital camera. That's what we have here. Digital camera, it's a basic digital camera might not be networked, right? It might just be an embedded system where you press a button, you take a picture, and the picture is stored locally, but it might not be immediately networked, right? So you would call that type of thing an embedded system because the complexity is embedded within the device. So a camera, an old camera, totally mechanical camera, has the same interface. You press a button, it takes a picture, right? New digital camera, same interface. Press a button, takes a picture, but there's a lot more complexity to what's going on inside. So that's the term embedded, right? The complexity is embedded inside the device, and the user doesn't have to see it. The user can benefit from the complexity, but using a very simple interface. Now, sometimes embedded systems don't interact directly with the user, but they interact with the user through another device. So what do I mean by this? Let's take this thumb drive, right? Now, a thumb drive, you've seen this type of thumb drive. It stores data. This type of thing does not interact directly with a user, right? A human doesn't connect this up to their body or something yet. Right now, they connect it to their computer, something like that, or their phone, or whatever it is, and then they interact with it. They can access the files on it through another device. So you would also call this an embedded system, even though it's not directly interacting with the human. And you see this in other devices like a car, the anti-lock braking system inside a car. That's interacting with a human, but not directly, right? The human presses the brake pedal, and the brake pedal talks to the anti-lock braking system. So the human interacts with the car, and the car talks to its subsystem. One big property of embedded systems and a difference in embedded system design is that efficiency is really important. So what that generally means is that it's not enough to get the design to work, to do its task. It has to do its task in an elegant, let's say an elegant way, okay? Either it has to do it fast, or it has to do it with low power, or it has to do it with at low price, right? So it's not enough just to get it to work. And this is actually a big difference between embedded system design and, say, traditional software design. So I teach programming too. When we teach programming, generally we just teach how you get something to work. Here, your goal is to get this code to do what it's supposed to do, whatever I want to do. Sort this list of items or something like that, right? But I'm not usually saying in that class, it has to sort this list of items and it has to use the minimum amount of memory possible. I'm not saying it has to sort these items and it has to do it within 1 second, right? I don't put these constraints on it. I just say get it to work. But with embedded systems design, you care a lot about the efficiency. You can't just get it to work, it's got to do it in an efficient manner. So what that means is that, the reason for these constraints is that most of these devices are used in cost-critical markets or in life-critical, right? So if it's used in medical or military, people's lives depend on these devices. And if it's used in cost-critical devices like consumer electronics, the cost is important. But either way, there are some constraints that are important to you. Besides just getting things to work, it's got to work within a tight set of constraints. So, for instance, say it's a consumer device, like a phone. So manufacturing costs and design costs and time to market, those things are primary. Because you want it to be cheap, right? You want to make money off the device, so the cost has to be low. Also time to market, because you have competitors. And this competitor's coming out with a new phone on this date, so you have to come out on the same date with a phone that's better than them, let's say. So those things are primary. But if, on the other hand, this is the military, this is going into a tank or a weapon system, and people's lives depend on it, and it's life critical, then you care about performance and power more. So if you're in the military, you might say, look, we'll pay millions of dollars for this device as long as it works and it can effectively do what we need it to do, right? So cost becomes less important, but power and performance really matter. And same thing with medical, right? You might be a lot more willing to pay a lot of money for a device, but it better work and it better maintain your heart the way it's supposed to, like a pacemaker. That thing better have high reliability, and it better control the pace of your heart properly. So if that means costing more money, then so be it. So in these embedded devices, there's always this tight set of constraints that you're working under. So it's not enough to get it to work. You got to get it to work within the set of constraints that you're given. So this is very different than traditional software engineering, where you just want to get it to work and get to work somehow. And the assumption there is that Moore's law will save you eventually. So by Moore's law, you may have heard of this before, but Moore's law just says that, let's say approximately says that machines get faster and more computationally efficient every year, right? They get more dense and faster, which, by the way, Moore's law is slowing down, but still, this happens. Machines improve. So software engineering, often you'll just say, look, just get it to work, and if it's slow, it's okay, because processor performance is improving every year, and so in the future, it won't matter, right? So that was the background assumption to a lot of software engineering. But embedded systems, you can't think like that. You have to think, look, not only does it work, it's got to be working fast, it's got to be working low power, and all this. Thank you. This lecture will talk about embedded systems a little bit more. We'll talk in more detail about how they're designed. Since that is the point of this course, we're going to be building IoT devices, which are embedded systems. So we're going to talk about differences in how you would design an embedded system as compared to a regular computational platform. And some of this we've talked about in the last module, but we're going to talk about how these differences impact the design process. Okay, so application specificity. Embedded devices are generally application specific. unlike desktop, laptop computers, which can run any type of program or pretty good at doing any type of program, embedded systems are made to do one thing or one related set of things. And we already talked about this with IoT devices. So, a phone sort of blurs that line a little bit, right? Because a phone can do a heck of a lot, right? You can run arbitrary apps on a phone. But most devices, like the camera in front of me, that thing is made to do camera, right? To record, playback, something like that, right? And it does all things related to camera activities. So that's common. That's typically how embedded systems are. And the reason why this is important is because it changes the way you design a device. When you know that the device is going to do one thing, you design it for the one thing. You don't design it for everything. So the design is focused on the one application, unlike general purpose systems like a laptop, desktop. So those things essentially end up being overpowered for whatever you have to do, because they have to be ready to handle any type of computational task. So for instance, take your standard machine, say quad core, right? 4 processors they have. Quad core is not uncommon. So you say you get a quad core, i7, something like this. It's running at 4 gigahertz, right? Generally, there is no way that regular users are using up all that computational potential of that machine. There's no reason why you need 4 processors to run Word or PowerPoint or whatever application you're running, right? You don't need 4 gigahertz to run these applications. So 99.9% of the time, these laptops and desktops are well underutilized. At 1% of CPU, some tiny fraction of their CPU is actually being used. But then every once in a while, you actually need them to do something. So say, most of the time, like say, cameraman right here, okay? He's got a Mac. I bet you he uses Photoshop or other kind of tools to do video processing, right? Now, when he does that, then it's using all the processing power, right? Because these video operations, effects on screen images, those require a lot of computational complexity. But 99.9% of the time when this thing is just running PowerPoint, something like that, that's not using anything. But every once in a while, it's running an application that really uses it. So in some sense, general purpose processors, most of the time they are wasted. There's no reason to have all that power, except in very rare cases. Maybe I'm playing a video game. Video games are another case where you really use a computational power because they're doing video operations all the time, graphics, complicated graphics. So when I'm playing my video game, okay, I need the processing power. But most of the time, I don't need it. So in some sense, general purpose machines are very inefficient in that way. And because of that, they cost more than they need to do any individual task. So what I mean by that is, say you want to play video games, and you want to play the newest, best video games. You can buy a computer, a good computer with a great graphics card and all this, and that might cost you $1,500, right, to get the newest, most up-to-date video card in the best computer to run the best games and run them fast. Or you could say, look, let me just buy an Xbox One or PlayStation 4, which is a lot cheaper, say $500, but it runs that game better, probably better than that more expensive computer, right? Now, all it does is games, but it does games great, right? It does games the best. So in this way, the design is much more efficient. It's being used to its full potential because all you ever do with the Xbox One is play games with that thing. So, and most of the time they're video. So you're using the capacity of that thing basically all the time. You're using it to, if not full, but at high capacity, as opposed to a general purpose machine. So this application specifically lets you change the way you do design so that you can just put in the things that you need to put in. Spend money on what you need to put in. So higher design efficiency is possible. So what that means is that if I know that I'm playing video games, there are certain pieces of hardware that I don't need in my design, right? Why buy that, right? If I know that, take this camera, right? This camera in front of me. I know that this thing is doing some types of video processing. I know it needs to control a lens and stuff like this, right? But it's never going to have to do other types of processing. I'm not going to be doing sorts or something, right? So I can change the way I do design to just include the software and the hardware that I need for the task that it's made for. And so that makes it cheaper. Now, it makes it more limited. It can only do what it's made to do, but what it does cheaply and efficiently. Another big difference in the way you design embedded systems as compared to sort of a regular desktop laptop is that hardware and software are usually designed together. So again, this is for efficiency reasons. But if, say you want to buy Microsoft Word or something, some typical desktop software, That Microsoft Word, you buy that completely separate from when you buy your computer. Well, actually, maybe you buy your computer and it comes with Word, but you can buy your computer and then you can buy Word completely separately. Okay? And there are two different companies. Maybe I bought my computer from Dell and I bought Word from Microsoft. Two different companies. One does the hardware, one does the software. Now, more and more, these companies are coming together, and sort of Apple is the epitome of this, right? They make their devices, hardware and software, together. They make the phone and the software, or whatever the device is, and the software as one, which means that they work together better, okay? And in fact, Apple machines traditionally are very reliable because of that. But it also makes them more efficient. So you can say, look, since this is just a phone, I don't need to be able to drive servos or something, right? I can make my hardware just the right hardware to run exactly the software that I need, right? You can match them. So your whole design process gets more efficient. And we're going to see this later on in the class. When we actually build these things, we're only going to buy the components we need to build the system we want. We're not going to say every system, oh, I'm going to put all this hardware and software together. No. We're going to buy, we say, well, we need this component, we need an LED, we need this, we need that. We hook them up, and we make this one system that we want and write code that uses only that. As opposed to a general purpose system where you have to have hardware for everything and software for everything just for the one occasion where you actually need it. So you're designing the hardware and software together, and that makes design a lot harder because you have to not only be a hardware designer, but you also have to be a software designer. So when you're writing the software, you have to think about what the hardware can do. See, normally when you take an application like Word, that thing, it runs on many different hardware platforms. You generally, as a programmer, do not have to be aware of this hardware platform that it's running on. You just say, look, as long as it's running on Windows, I don't care. Right? And actually, it doesn't even have to run on Windows. It can run on many different applications, and you don't care about that as a programmer. But if you're writing code for an embedded device like a cell phone, you have to know exactly what the hardware can do. You have to know, I have a screen, it has this size, right? So I'm limited in how I write my software to use up that area, right? I have touch sensors, which can sense this and that, right? So I got to place my buttons so that everything can be touched. So you have to really be aware of the hardware when you're designing the software, and vice versa, which changes the design process and makes it, frankly, more difficult. Yeah, so more work for designers because you have to understand some of both. Thank you. This lecture, we'll talk about the structure of an embedded system, the hardware structure specifically, look at the different components in a very generic view, the different types of components, and we'll talk about some of them. The main component, the microcontroller, we'll talk more about in the next lecture. So here's my high-level generic view of what an embedded system looks like. So if you look at an embedded system, it's got to take data from the outside world, and then it's got to output data to the outside world. So it has, first for the receiving data from the outside world, it has a set of sensors. So these sensors, they receive information from the outside in many different ways because there are lots of different types of sensors. The most basic type of sensor would be a button, push button, something like that. And that's receiving data that somebody types in, 0 or 1, it's binary. Then there's also, let's see, for instance, you could receive sound information like the microphone in front of me, or actually connected to here. And that receives audio information. There's also video, like the camera in front of me, or just a regular light sensor that receives video information. There's all kinds of sensors. Touch screens, right? You can receive touch information through a touch screen. So there are a lot of different sensors that an embedded system can receive input from. So that input comes into the set of sensors, and it's going to go into the core of the system. And in the end, once the system has decided, processed that information, decided what to do with that information, it needs to cause some result, some effect to happen in the outside world. So that's done through the actuators at the other side. The actuators, they cause events to happen in the real world. So those might be something like an LED, a light. Like there's a light flashing in front of me. That LED is an output actuator. And it goes off and on to indicate probably that it's recording. Okay. But there are other actuators too. Like for instance, the camera in front of me, it's got motors inside that control the lenses to control the focus. So those motors, those are actuators. Those are outputs of the system. So the system will drive those motors, and those will be considered actuators and make them pull the lens in and out and things like this. So lots of different types of actuators. Speakers are actuators, right? They output sound. Lights are actuators. They output lights. Screen is an actuator. It also outputs light, but in a more interesting, I don't know if you call it interesting, but a more detailed format, more complex format of light. So a screen is an output. So there are lots of different actuators. So if you look at the embedded system, it's in between there, right? It receives data from the sensors, it does something with the data, and then it outputs to the actuators to make something happen in the real world as a result of the data that it received. So the interface components are the sensors and the actuators. Now, in the middle of the system, the center of the whole thing is that microcontroller in the center. Now, the microcontroller we will talk about in the next lecture in more detail, and actually a lot of this class, this specialization, will focus on microcontrollers and how to program them. But there are other components that are commonly inside the core of an embedded system as well. And you see two of them right there, IP and FPGA. We'll talk about those in a little bit right now. So IP stands for intellectual property, or IP core, people call them. An intellectual property core is basically a pre-designed component, typically a pre-manufactured component, so an integrated circuit, a chip, that performs one function. When I say one function, maybe a set of functions, but all related to one particular task. Okay? So it's a chip that is not general purpose programmable. It's a core that just performs some small set of functions that are all related. So these things can be very useful. They're cheap and high volume. So what that means is, high volume means manufacturing volume. So if you have some very common task that's performed by a lot of systems, like say you got a cell phone, right? And in that cell phone, let's say it's very common to perform some type of audio filtering task, okay? So all of our cell phones have to do this audio filtering, right? Let's say. So you might make one of these IP cores which performs filtering. And it would be high volume because there are many millions of cell phones that are for sale, and so you manufacture many of them. So there's a lot of work to designing one of them, and it costs a lot if you want to just fabricate one. But when you're fabricating in high volume, it's very cheap. So these IP cores can be very valuable when you have high volume production. So they're useful for common tasks. That's the best thing. In order to make sure you get high volume, you basically want to have you want to use them for very common tasks that happen over and over, so there's a lot of need. So if it's just a one-off, if it's a design, some kind of function that's only done in this one system, then you would almost certainly not make an IP core and make a special purpose chip just for that. You wouldn't do that. But if it's some common task that's done a lot, so for instance, network controllers, right? That's in a lot of systems. Basically, every Internet of Things device has some sort of network controller in it. So that type of thing you might implement as an IP core, dedicated piece of hardware which just does IP control operations. Audio-video codecs, right? So encoding audio and video and compressing it and decompressing it, right? These are operations that are performed by lots and lots of IoT devices. So this type of device, this type of function you might put into an IP core. Now these IP cores, we're not designing them in this class. That's outside of the scope of the class. But when you're making an IoT system, you definitely might want to buy one of these. So you'll look at a library, an online library of IP cores, find some vendor, Texas Instruments say, they sell a lot of chips that do different things, and you find the one that does exactly what you want. You say, oh, I'm doing MPEG encoding. Let me find the TI MPEG encoding chip, and you'll probably find 50 of them, and you pick the one that you want, and that's the core that you use. So, so that's how we use these things. We're buying them off the shelf. We're not actually going to be designing IP cores because that's too complex. And they have to interact with the microcontroller. So remember that the microcontroller is the center of all the action, right? So it's connected to the IP cores, and it tells them when to do what they need to do, right? So if an IP core is for encoding video, the microcontroller will say, encode now. Right, encode this data now. And when I say it will say that, I mean through the signals, through the wires, it will send the appropriate sequence of input signals to trigger it to record. Right, and then the results, maybe the core sets the signal high when it's completed, and that goes back to the microcontroller. Microcontroller knows, okay, encoding is done. Let me move on. Right, so there's this conversation between the microcontroller and the IP cores that goes on, and so you have to wire it appropriately, and we'll only touch on that. Now, another component that you often find in IoT devices, embedded devices in general, are field programmable gate arrays. Now, we will not be using field programmable gate arrays in this class because their complexity is basically outside of the scope of the class. But what they are, they're an interesting thing. You should know what they are. They're hardware. They're integrated circuits, the chips. not programmable chips. They're regular chips. They're not programmable in the conventional sense. Okay, these things can be reconfigured, essentially rewired to perform different tasks. So let's say you need something to do audio filtering. So you might configure the FPGA to perform filtering. So it's a hardware device that will perform filtering because it's been wired to do that. But then you can rewire it, reconfigure the device to rewire it so that it performs MPEG encoding instead or something like that. So you can rewire this thing, reconfigure it so that it can perform different tasks. Now, it's not programmable in the sense of a general purpose processor. You don't write code for it. And as a result, it's actually a lot faster than a general purpose processor, right? You could get that same flexibility with a general purpose processor. You could run one program or run another program. You could do that with a processor, but you would do it with an FPGA if possible because it's a lot faster. It'll execute a lot faster. Because there's a software conversion step that we won't talk about here that is skipped if you do it directly in hardware using an FPGA. So FPGAs have that advantage. And no fabrication is needed. See, when you make an IP core and you fabricate it as a chip, you have to fabricate it. You have to manufacture chips, and that's expensive. So it only makes sense in high volume. With FPGAs, you don't have to fabricate. You just reconfigure it through programming. Just connect it by USB up to a computer, and you can rewire the thing. So that's much more convenient and cheaper. So if you have a one-off design, you would implement it in an FPGA over some sort of an IP core. Thank you. This lecture will talk about components in embedded systems, the hardware components. Specifically, we're going to talk about microcontrollers. We'll start talking about microcontrollers. We'll go on in the next lecture about that too. The microcontroller is the center of the action, so good to start there. That's where we'll be mostly focusing this class, really, is working with the microcontroller. So here's a picture of a board, an Arduino. There are different versions of Arduino boards. But and you have one, or you may have one. This one, this particular board, you can see there's a big chip in there, that black chip over there, and like the bottom part of the board, and that's actually the microcontroller itself. And there are other devices on this board, but the microcontroller is that main chip in there that's going to be executing the programs that we're going to write. So note that the Arduino board, we'll go into great detail about the Arduino board in the next course, but the Arduino board has a lot of other stuff on the board to support the microcontroller, but the microcontroller is that particular chip right there. So a microcontroller is an integrated circuit that executes a program. So this picture of microcontroller looks a little bit different than what we saw before. That's actually the bare silicon. So we're not going to go into depth about how these things are made, but these chips, they're made out of silicon, a semiconductor, mostly silicon. Ours are silicon. And so there's a wafer, a small chip. That's actually what the typical chip looks like. But that's not what you use. It's not in a usable form yet. Before you can actually connect that to anything, you have to actually wire it up. You have to package it, what's called packaging. But that is a microcontroller, and it will be packaged, and then it's going to be integrated into the middle of the system. So the microcontroller, its job is to execute code, and it's the center of the system. So it reads inputs from other components, and it controls other components. Microcontroller versus microprocessor. So it's a terminology difference. Basically, the way I think about it, I don't know what the formal definition, but I know how it's commonly thought of. A microcontroller is basically smaller and weaker than a microprocessor. So when you say microprocessor, you're thinking about what you would find in a desktop, laptop, Intel, whatever, AMD, whatever. Big general purpose processor, general purpose or digital signal processor. That's called a microprocessor. Basically, they're more heavy duty. They're very fast, have a lot of memory and all this. A microcontroller is more slimmed down, okay? More like what you would find in an embedded system or an IoT device. Because remember, these devices, they have to be designed efficiently, right? We don't want overkill. We don't want to over-design the system. We don't want to buy the highest end processor, quad core, 4 gigahertz, whatever the highest end is at the time. We don't want to buy that if we don't need it, right? For the tasks that we're performing, maybe we're interacting with users, and these users are only so fast, so maybe you don't need a fast processor. So you want the cheapest processor that will do the job. So you will go for a microcontroller which is slower and cheaper than whatever the high-end microprocessor is. So a microcontroller is generally, think of it as a lower-end microprocessor. Roughly, that's what it is. So it's slower. Typical, this is, by the way, these speed numbers are completely, they change over time, but common ratio. So a microcontroller might be 16 megahertz. That's a slow one. You can go slower than that, 8 megahertz, something like that, 4. All the way up to, well, I have 500 megahertz. 500 megahertz is sort of a high end. Actually, though, if you look at, say, a Raspberry Pi, that's going 1 gigahertz, I think, so it's twice that. So it's a shifting scale, this range, okay? But generally, microcontrollers are going to be slower than microprocessors and going to have less memory, less of everything, roughly. Less memory, fewer features. So there are lots of other features, and we'll talk more detail about these in the next course. Specifically, we'll talk about Arduinos and Raspberry Pis and the processors, the microcontrollers that are on those devices. We'll talk in detail about what features they have, but they are less than the features that you find in your standard microprocessor for a desktop, laptop. So this picture, this shows a microprocessor in, after the silicon has been packaged. So that, you see it's a black rectangle, black square in this case, right? That black is all packaging. And that packaging is basically to keep the chip safe. Also, it cools it, so it helps propagate heat out because these things get very hot. Also, you'll notice around the perimeter of the chip, of the circuit, there are these pins. They're called pins. These little pieces of metal, essentially, that are used to wire it to the rest of the components in the system. So if you look at that picture, it's a printed circuit board, a little piece of one. Actually, this is the back side of one, so we can't see all the parts on it. But there are lots of other parts that this microcontroller, microprocessor is wired to through the printed circuit board. We're not going to actually build printed circuit boards in this class because that costs money we're not going to spend. We're going to do this type of thing, this wiring manually. But in a printed circuit board, there are what are called traces, little pieces of metal that are drawn onto the printed circuit board, connecting different components. So the microcontroller is at the heart of the system. It's connected to lots of different components that are in the embedded system, in the IoT device, and it takes inputs from them and it sends control data out to them. Now, microcontroller needs to be programmed. It needs to run code. That's what it does. It executes code. So you need to write the program in some language. Now, there are many languages that you can write programs in. We will be using, well, when it comes to Arduino, we'll eventually be using C, C++. And then when it comes to Raspberry Pi, we'll be using Python. But you can use different languages. But at some point, you have to write a program in a language. And then that program has to be compiled or interpreted, and we'll talk about that in another lecture. And the result, though, has to get transmitted onto the memory of that microcontroller. So it has to be placed in the memory of the microcontroller. So inside that microcontroller, there's always some flash memory. Flash memory is just a non-volatile memory, memory that stays after you power it off. So there's some memory, and that memory has to hold the program, so that when it gets power, it starts executing the program from the start. And we'll be doing that in the course of this course and the next course and all the rest of the courses. So the microcontroller has to be programmed. So this term programming, in terms of a microcontroller, means when you write the code. So first you'll write your program on some host platform, a laptop, desktop, which is not the program that you're going to execute, not the chip that you're going to execute it on, not that microcontroller. You typically write the program on a different host processor, like your laptop, desktop. So you write the program there. Then you process the program, compile or interpret the program, or compile it and then interpretation will happen later, but you compile the program. Then that final version of the compiled program has to get transferred to the microcontroller. Usually it's done through a piece of hardware, an external piece of hardware. So here we see in the middle, there's a little board. That board is connected by USB to the laptop, and the microcontroller chip on the side of the diagram, that is plugged into the board. So there's a slot that fits the microcontroller. You plug it into the board, then on the laptop, you would hit program, there's a button that hits program. You program it and it'll write the data into the memory of that microcontroller. So that's one way to do it. Now that is not exactly how we're going to do it, because we're using an Arduino and Raspberry Pi. We'll show that later. Basically, the way an Arduino and Raspberry Pi work is that a lot of this programming hardware that you see in there, that is built into the Arduino board and to the Raspberry Pi board. So we don't need a separate device to program the microcontroller. That logic is basically built right into the board. So we just take our Arduino Raspberry Pi, plug it in by USB into the laptop desktop, and we can program it directly. Thank you. So in this lecture, we'll talk about basic components that you see in embedded systems commonly, different versions of what you will eventually use in the class. So development board is very common. On the development board, you see circled in red is a microprocessor, microcontroller actually in that case. It looks like a Freescale. Yeah, and this is a board from my office actually. This Freescale board has a Freescale processor on there, and you can program it from a host. So you go to a host like that laptop that's pictured there. You type in the code, you compile the code, and you connect the host to the development board and transfer the data to the microcontroller. So you usually do your programming on the host. Not always. Like with a Raspberry Pi, as we'll see, you can actually do the development on the Raspberry Pi itself if you want to, but it's most common to do it on a host because a host is generally a more powerful platform, easier to program on. So as far as processors go, there are, and microcontrollers as well, but right now just talking about general purpose processors, you can classify them in, say, two broad categories: general purpose and digital signal processing. So general purpose processors, those are what you see in your standard desktop laptop. They're used for any application, and they include many features, but they're overkill for most features. They have many features that you probably don't even need, but they can handle anything. So any particular task, they can do it. They can do it adequately. But they tend to be more expensive because they're over-designed, right? They're over-engineered, and they have many features that maybe you don't need a lot of them, but they have it just in case. So that's a general purpose processor. There are also digital signal processors, which are specific to doing digital signal processing applications. So digital signal processing is basically processing data streams. So audio streams, video streams. These are common. These are very common. You know, maybe you want to, as audio is coming in, you want to filter that audio, or you want to compress that audio. Or same thing with video. Same thing. You might want to filter it, or do some special effect, or compress it, or something like that. So these are big streams of temporal data over time, and you want to do some processing on it. Digital signal processors are actually good processors to do that with. And they're made for that, with that in mind. They have special instructions for that. They have what are called vector instructions. So vector instructions are instructions that do the same thing to lots of different data. So for instance, say you got add, right? With add, you might take two numbers and add them together and get a result. So a vector add might take 32 numbers, add them to another 32 numbers, and get a 32 number result. So it just does the same thing for many pairs of data, many sets of data. And this is very common in signal processing. So imagine you're processing video, right? You got some image with 1 million pixels, which isn't even a lot. And you want to perform some blur or some operation to the pixels. Whatever operation you perform to one pixel, you want to do that to all 1 million, the same thing. So vector operations are very useful for things like that. You can just do things in parallel very quickly. So sensors are extremely common. You need some form of sensors, and sensors just receive information from the environment. There are lots of different kinds of sensors. Let's generally say you can have simple sensors that receive, say, heat information, like thermistor, that receives temperature information. Photoresistor reports light intensity, right? So these are generally simple sensors. I'll call them simple sensors because their inputs and outputs are just real numbers, right? 0 volts to 5 volts, right? So it's bright or it's not bright, something like that. But complex sensors can actually receive much more complicated data. So for instance, take a camera, a CMOS camera, a camera in, like in a digital camera. So it captures images. Now that's a light sensor. It's technically a light sensor. It's a special purpose light sensor. It doesn't just tell you the intensity of light like a photoresistor might. It also tells you what color the light is at every point in the image, right? So it's much more complicated visual data that this thing is reporting. So it can't just give you one number, 0 to 5, yes, this is bright. No, it's not. It has to give you, say it's a megapixel, a million pixels of image data to represent what it's capturing. So this is a sensor. It's still receiving data from the outside world, but it's a much more complicated sensor. So there's a lot more data to receive, and it's more complicated to work with generally. Now, we can still work with them, but you generally have to know a little bit more about the circuitry in order to do that, or use library functions, which we will talk about later. Now, also an Ethernet controller, you can see that as a sensor. Whether that's a sensor or not is a question. It's a sort of a judgment call, but an Ethernet controller will allow you to receive information on the from the network. So that information, you can call that sensing, not necessarily from the physical world, but sensing from the network. So, and the type of information that we receive over the network can be very complicated. So that's a more complicated form of a sensor, more complicated to use. Actuators, they cause events to occur in the environment. There's some simple ones. LEDs, light emitting diodes, they turn lights off and on. LCDs, displays, liquid crystal displays, that's like what's on my digital watch, right? You've seen these. They're not backlit, so they're not as bright. But they're low power, but they're useful. And so those that you can put numbers on them, something like that. So that's a relatively simple display. You can also have more complicated actuators, like a servo motor. So there are motors, DC motors. Servo motors are a little bit more complicated. You can control the angle, the precise angle to which the motor turns, which is useful in a lot of cases, like, say, a robot arm or something like that. Ethernet controller can also be thought of as an actuator because it can output data to the environment. If I consider the network itself to be the environment, then an Ethernet controller allows you to output some messages, some message data to the network and send it out to wherever you're going to send it to. But these are more complicated sensors, or actuators, I'm sorry. Thank you. So we're going to talk about analog versus digital. If you remember, several lectures ago, we talked about embedded systems, IoT devices, and their interface. And so at the inputs, they have a set of sensors that receive data about the outside world. Though the sensors could be simple things like buttons or something like that, but it could be a microphone, a light sensor, a camera, something like that. But it senses data about the outside world. And then actuators on the other end output data to the outside world. So maybe they're lights, LEDs, or speakers, or or just a screen or something like that. Okay, but they send data to the outside world. So there's this interface: sensors and at the input side, actuators at the output side. And so these devices, they're sensing physical phenomena. Okay, so if you look at the sensors are sensing physical phenomena, and physical phenomena are often analog signals. Okay. Now, let me describe this difference between analog and digital just very briefly. Analog, actually, a very quick way to say it is, analog to digital is the same as the difference between real numbers and integers. Okay, if you remember that, right? Real numbers are continuous. So if you look at the number of real numbers between 0 and 1, there's an infinite number of real numbers between 0 and 1. 0.5, 0.6, 0.7, whatever fraction you can think of, that's an infinite number of values, of real values between 0 and 1. Now, integers, however, can only be 0 or 1 or 2 or so on, right? No fractions. So between 0 and 1, there's just integer 0, integer 1. It's a finite number, right? And a much smaller number. So no fractions. So that difference between real numbers and integers is the same as the difference between analog and digital. So if you look at an analog value, let's take light, okay? I've got a lot of light, got these lights pointing at my face, okay? Lights, generally they have analog values. The brightness has an analog value. So you can take a light and have a dimmer switch connected to it and make it a little brighter or a little darker, right? And depending on how fine your control is, you can have a lot of possible values between totally off and totally on. And it's a smooth transition. You can hit every possible value between completely dark versus completely bright by turning your dimmer switch. So in this way, light is generally an analog phenomenon. Also sound, you can see the same thing there. Sound, I'm talking, right? I can talk quietly, I can talk loudly, right? I can talk in between. So I can adjust my volume anywhere in between completely quiet, completely loud. Again, an analog phenomenon. So the universe, the world in general, to the perception of humans is analog. Now, physicists will say, look, it's a digital, the world is digital. Like if you look down to subatomic level, look at quarks and they have fixed states. Maybe things are digital in reality, okay? They are discrete, either as high or low, plus, minus, right? Maybe. But to our human perceptions, the world is analog. So a lot of these phenomena that you want to sense are analog. Sound, touch, right? You can push hard, push soft, things like this. They're analog phenomena. Now, digital phenomena is something that's either off or on, or at least has some discrete number of states. So for instance, these lights, I could just hook them to a switch. They're wall switches, right? I hit off and the whole thing goes off, or it goes on, right? So maybe I'm using my light in a digital way. It's either all off or all on, right? That's digital. Or that's discrete, really. And digital is a version of that. But so that's basically the difference between analog and digital. This is also, you get the same definition in terms of watches, right? So my watch is a digital watch, right? It shows digital numbers, 1 second, 2 seconds. It doesn't show fractions between seconds. But if you look at an analog clock, where that second hand is, can point at any fractional number between seconds, right? So this is analog to digital. Now the reason we bring this up is because these embedded systems are interacting with the real world. And the real world, to our perceptions, is largely analog. So say I want to have a sensor that senses the brightness of light. That sensor is generally going to be an analog sensor because it's got to be able to sense, assuming that the light is not either off or on, it could be a little bright, a little dark, it's got to be an analog sensor. Now the problem with this is that our systems, the microcontrollers that we have, they are digital systems. So they only understand digital data, specifically zeros and ones. Okay? Zeros and ones, binary data, that's binary, 0 or 1. That's digital. So in order for our program on our microcontroller to be able to use information from sensors, that analog signal has to be converted to a digital value. And that is what analog to digital conversion is for. So we're not going to talk in great detail about how it's performed. Now, I have a slide where I'll show you a little bit about it, but how it's performed is a complicated thing. But just understand that what it does is it takes an analog value and converts it to a digital number. Now, this digital representation is maybe an approximation of the actual analog value, but that's okay. It can be a pretty accurate approximation, as accurate as we need. So we need analog to digital conversion at a lot of our inputs. Not all. Some of our inputs can be buttons, like push buttons, right? And then that's actually naturally digital. It's either pushed or not, so 0, 1. But other analog inputs like lights and sounds and stuff like that, those things typically have to go through analog to digital conversion before they can be used in our system. Now, on the output end, you usually need digital to analog conversion, or you often need digital to analog conversion. So let's say I have a microcontroller and it's outputting some sound to some speakers. These speakers are analog devices. They need analog signal. But the microcontroller is outputting zeros and ones. So you need digital to analog conversion to take those digital signals, convert them to analog, and then drive the speaker with them. So it's very common to see digital to analog conversion on the output of a system and analog to digital conversion on the input. Because in the middle of the system, in that microcontroller, it's almost all digital. It's primarily digital. So and the world is often analog, so you need conversion on either end. So just to give you a little example of how you might perform analog to digital conversion. You take some analog signal, a waveform over time, and we see one right here. This is, let's say it's a sound wave, okay? So if it's a sound wave, sound is pressure through the air, and it changes over time. So you can measure sound waves, you can look at sound like we're seeing here in this picture, where the x-axis is time, and the y-axis is pressure in the air. And that's actually a sine wave that you're looking at right there. So that's like a pure tone. One frequency, just a woo, a frequency as pure as you can get, that's a sine wave. That's what it would sound like at some frequency. So the y-axis is generally the pressure, the air pressure. Now a microphone, the job of a microphone is to take that pressure and convert it into voltage, okay? Because our machines can't understand pressure, they understand voltage, they read voltages. So if you look at the y-axis as it's labeled, it says voltage, and then in parentheses, pressure. So what they're showing is the voltage at the output of the microphone. But still it's an analog waveform. It's smooth, the red line, it's analog. And it changes smoothly over time. Now, the analog to digital converter will take that waveform and represent it piece by piece as a set of digital numbers. So you can see that so if you look at that red waveform, It's smooth. It's real numbers. It's an analog waveform. Superimposed on that, you see the stair-stepping, basically essentially just a stair-stepping signal that's always has discrete values. So there are those levels, those horizontal lines. Each one represents a discrete digital number. And 1, 2, 3, 4, 5. And if you look at that stair-stepping waveform that's overlapped on top of the analog waveform, it only ever hits one of those lines. It's never in between, right? It's at a line or up or down, right? That's digital. So you can take this analog waveform, this red one, and approximate it with this stair-stepping digital waveform. And so at every unit of time, the digital waveform is always at a fixed voltage value in this case, right? And so you can just have a series of voltage values over different points in time and store it, and that is an approximate representation of this analog waveform. And that is what analog to digital conversion does, and we need it in order to represent any kind of analog input data to the system. And note that on the outputs to the actuators, you get the opposite going on. So you start with the digital waveform, the stair-stepping waveform, and the digital to analog conversion converts it into that red, or something close to that red, smooth analog waveform that you see, and that gets sent out to whatever your actuator is, say a speaker or something like that. Thank you. So in this lecture, we'll discuss some of the basic equipment that you're going to be using when you're building your Internet of Things devices. And some of the basic equipment that we'll be talking about through the class, we'll assume that you're using. Just to make things a little more concrete, so you see, I've been more generic earlier in the earlier lectures about what the general type of equipment, but now we'll actually point to the specific things that we were going to cover in this class. And then when you do the capstone, you'll be using this type of equipment when you do your capstone. So first, the main thing we're going to use is a development board of some kind. It's a board that has a microcontroller on it, okay? And which is, of course, the center of all these projects. The center of these systems is going to be some microcontroller with some code running on it. So the picture that we have here is actually an Arduino board, and that black chip on the board is actually the microcontroller itself. Now there's other hardware on the board. There are interfaces, like for instance, you can see a USB interface on the side. There are a bunch of holes on the side that you can't see yet, but those are plugs where we're going to plug wires into. We'll do that later. There's power, and often there are other interfaces on the board. So there are other interfaces on the board. There are also other chips on the board and other devices on the board. So there's the microcontroller, but there are other things that are used on the board. Generally, those development boards, what they are, for the most part, the main thing they have to have is a microcontroller that you're going to program, but also hardware on the board to program the microcontroller. So basically, data has to get taken from the USB cable typically. So this has a USB port. It has to get taken from the USB cable, which is connected to your host. It has to get taken from the USB and programmed into the flash memory of the microcontroller when you want to put a program onto the microcontroller. So typically, these boards are minimally, they will have equipment on there, hardware on the board, whose job it is to read the USB cable and take the data that is received on there and program it onto the microcontroller. That's sort of a minimum thing that you're going to find on these development boards. Now then, a lot of different development boards have lots of different extra equipment in addition to that. Maybe you have compasses, accelerometer, magnetometer, all sorts of extra components you can find on these boards, touch-sensitive screens, all this stuff. But the basic board is just what I'm talking about right now. And the boards that we're using, certainly an Arduino is pretty basic. It has basically what I just said, and that's an Arduino right there. It has very little else besides the microcontroller, the hardware used to program the microcontroller, plus the interfaces, USB and the pins and stuff like that. That's basically all an Arduino has on it. Now we're also going to use a Raspberry Pi, and we'll go into that in more detail later. That has more things on it. That actually has an accelerometer on it. It has a magnetometer, meaning a compass. It has a few other things on it, but it's mostly pretty bare. It has a processor on it too, a microcontroller on it too. I would say it's a higher end microcontroller than what you find on Arduino. But that's the core of the system. So that's how we're going to start. We're going to take these development boards, plug them in by USB to our host, our laptop, desktop, write code on the laptop desktop, program it onto the microcontroller on the development board. Now, other equipment you're going to get. USB cable, clearly, just to connect the board up. Ethernet cable is a common piece of equipment. I don't know if we'll be using that, but Ethernet is common because a lot of these boards have Ethernet cables, have Ethernet jacks, because we want them to be networked, right? We're talking about Internet of Things, so it's common to have an Ethernet jack. Raspberry Pi does, standard Arduino does not, but it's common that they have Ethernet jacks, and then you would need an Ethernet cable to connect to that. Jumper wire, so you're going to need a set of wires. You'll get a set of wires to plug into the input pins of the board. So that Arduino that we saw in the last slide, it had several holes. You can plug wires into those holes to connect up other things. Different inputs. These are components that we will commonly use as input components, so essentially sensors. So a potentiometer. A potentiometer is a sensor that senses how much turn. It senses rotation. So if you turn something more, it turns to the left, turns to the right, it changes the resistance between two signals. And you can use that as a rotation sensor. So if you want to implement a volume knob or something like that, you can use a potentiometer and sense how much is turned. Photoresistor, so that's something that senses the brightness. So the brightness of the light will change the resistance on a certain resistor, and you can sense that. Keypad, that's another common component, just a bunch of buttons put together. Buttons, individual buttons, that's another common piece of equipment, and we'll have some of these. Some of the outputs, LEDs, so those are light-emitting diodes. You've seen those little lights that turn off and on, light-emitting diodes. Resistors, we'll talk about those later. They don't do much. They consume power and they change voltage for us, but simple components. We're also going to use a breadboard. Now breadboard, actually I have a picture of that on the next slide. So breadboards are for wiring. So we're going to have a bunch of these components, and we're going to need to connect these components together. And so how do we connect them? Well, there are several ways. One way is to solder things, and we are not going to do that. Soldering is a more permanent connection, where you take two pieces of wire, two pieces of metal, you want to connect, you take an iron, a hot iron, touch it to the joint, you bring some solder, which is softer metal, you melt it onto the joint, and it forms a seal, and it connects them electrically. So that's soldering. We won't do soldering because soldering, well, several things, but the main thing is soldering is more permanent, and we're just prototyping, right? I mean, you're going to be trying things and trying things again, making mistakes, trying again. So soldering is too time-consuming. Soldering is more permanent. In the end, when you're done, you know everything works, then you might solder things together. But we're not in that mode. We're going to be using a breadboard. So breadboard is for permanent, non-permanent wiring. So basically, it's got a bunch of holes, a board with a bunch of holes. And these holes fit 24-gauge wire, which is the common wire size for components like this. And these holes are connected electrically. So there are rows of 5 holes you can see there. And if you put a wire into one of those, one hole in a row of 5, all the other holes in the same row of 5 are connected. So you can plug 2 wires into 2 different holes on the same row of 5, and they are connected. And that's how you connect components. So you can plug one connection from a component into one hole in the row and plug another component into another hole in the same row, and then those 2 components are connected. Okay? So this is how we're going to be doing wiring. We're going to have our breadboard, and we connect things in that way. And if you look at the breadboard, it's got these rows of 5, but then along the left and right sides, you got these columns, right? These 2 columns on the left, 2 columns on the right, with breaks in between, but basically 2 on the left, 2 on the right. So those columns are actually wired differently. They're not wired horizontally like those rows of 5. They're wired in columns. So those 2 columns on the left, all holes in the same column are connected to each other. Then all holes in the next column are connected to each other. Same thing on the other side. All holes on the one column and all holes on the next are connected. So traditionally, those columns are used for power and ground. Because usually, when you make a system, you have a lot of chips and a lot of different components in there, and a lot of them need to receive power and need to be connected to ground. So it helps to distribute power and ground across the whole circuit, to just put power and ground into those rows, those columns rather. So put power into one column, ground into another. Then anything you want to connect to power and ground, you don't have to run a long wire, you just run a wire straight to that column, to the nearest hole on the column. So we'll be using breadboards to connect up our components. And you know, it's very common for prototyping, and it's made at a specific size. It's a common size. Here's a typical circuit. This is just one possible circuit, but there's an Arduino. And this Arduino, it's connected to some LEDs. You can see those red LEDs that are in the breadboard, right? So the LEDs are plugged into holes in the breadboard. They have two leads, so an LED has two leads, two wires. They're connected to holes in the breadboard. There are also resistors. I don't know if you can see them, but those little components that connect from the LEDs to the bottom row, those are called resistors. And we'll talk about that circuitry. Basically, you always want to put an LED in series with a resistor. If you don't, then what will happen is you'll drive too much current through the LED and you'll blow it out and it'll burn out. It'll be very bright for a second, then you'll hear a pop and it'll be gone. So you put resistors in there just to slow down the current, basically to reduce the current. Not slow it down, but to reduce the amount of current that goes through. And the other side of the LEDs are connected by those blue wires into the Arduino. And the Arduino has some program running on it that probably turns on the LEDs, turns them off and on in a particular sequence or whatever you want it to do. So those are the type of components that you will be using in the class and we'll be talking about in the class. Thank you.